Okay, let's begin today. Let's begin. I hope everyone had a good weekends. So I think I already gave you another assignment last week, 그죠? Assignment 3 is up on the 한양인, so you can check if you haven't checked it yet, which is due probably sometime next week. So there will be another small written assignment soon this week, and I don't think it will be a problem. About the midterm, I'm still in the way of marking them, so hopefully I can finish it off sometime this week or early next week. As soon as I finish marking your midterm exams, I will upload your marks and averages and stuff, so you can find out where you are in your midterm exams. Okay. Anything else? 모르겠다. Have you guys started taking a look at the assignment 3 yet? 그 web pages, right? I mean, you can finish up pretty quickly, but just in case if you're not very familiar with the idea of having your own space in the cloud and having a free web pages, or someone might be interested in getting the domain names, then it would be better to start early sometime this week so you can finish it off on time. Okay, so still we're gonna continue on the networking internet part. Before we discuss on the networking, we discuss on the algorithm for shortest path algorithm, 그죠? Dijkstra's algorithm, which now I'm thinking we should have done this first and then go to that Dijkstra's algorithm, because finding a path between two nodes will be the similar idea in the internet that finding a path between two hosts, two persons through the internet, which will come up as a connection models that you can try different algorithms on top of it. So many of this stuff that we already know, I think I discussed a few stuff like if you want to increase your network sharing devices, NAT, 그죠? 공유기, there are a bunch of different standards that you can try on in order to, from those NRU website we looked at, if you want to reach up to 300 megabits per second, they usually say something NGBC, those type of standard that we discussed. It's actually its name is actually go like IEEE 802.11bgcn as that number, as it has a new number, usually referring to a faster speed of the Wi-Fi, and that's more familiar with us. And I think I explained briefly about LTEs, but those are gibberish. Anyway, let's take a look at what your textbook is discussing in terms of very basic skills, very basic technologies for internet and networking stuff. So again, computer network made up of computing devices, node and interconnections. Network may be wired and wireless communication link using various techniques. Network is actually a process-to-process communication in your systems, right? You like to exchange a data between your friends, which is in two separate computers, programs running on that computers, and they like to exchange the messages between them. So it's computer networks. Wire, dial-up, broadband, we know, the modems that we know. Broadband, which is the typical connections that you can buy from ISPs, internet service providers, things like, 우리 뭐 있지? What is internet? Where can you buy the internet connection? Which companies can you buy from? 어떻게 여긴 아무도 안 왔네. 그죠? Something is not right. KT, SKT, those type of companies. Sometimes they're referring to as an internet service provider, or they sometimes referring to as telecommunication companies, or shortly referred to as a telco. telco라고도 부르기도 하고. So you can buy from them. Wireless LAN, wireless LAN, WWAN, we're going to take a look. And then we look at this graph. You actually try to put this digital signal 010 onto top of this analog signal. That's what is modem is doing. Different modularization techniques are bringing up the better speed of the modem times. Still effective. This is brief picture. Try to explain that ideas for. They try to mimic the 1 and 0s using the signals and blah, blah, blah. That was encoding example. I think we looked at around there. And DSL that you're very familiar with, cable modems too, shortly referred to as SO providers too. 그죠? 우리나라에서는 SO 사업자라고 많이 하죠. SO it's so called as a cable providers. Actually, they are the competitor. DSL, FTTH, fiber optics, usually from a telecommunication providers. Cables. 집에서 케이블은 어디서 보지? 동네 케이블. 그죠? SO providers. They also provide internet services too, right? So they try to compete each other. Who's offering a high-speed internet in what price? Usually that's a selling point. Anyway, we all know this. I'm going to skip a few slides. And then basic networking concept continues. Commercial and institutional users, people like us, university in 1970s, they start using something called Ethernet. Last week, I asked you about what is this cable called? 이거. I was asking for a name of this cable, and someone told me internet connection cable. That's also right, but it's actually, to be more exact, it's called Ethernet cable. Ethernet is a protocol name, which is pretty much everyone's computer, Ethernet port, the place that you can plug in those cables. 그죠? Those are popular choice. 1970s dedicated coaxial cable. Coaxial, what is a coaxial? Okay, 구리선. 이렇게 꽈놓은 거, coaxial cables. Operate at 10 megabits per second. Mbps means bits per second. Bits per second. Megabits per second. That's how much you can send 10 megabits per second. Your cables, your current internet connections in your desktop, what is the usual speed of your Ethernet cables that can plug in? 자기네들 쓰는 랩탑에 일반적으로 속력이 어느 정도까지 나오는 케이블이 들어가죠? 응? 아니야, 와이파이 말고 선, cables. We haven't touched it yet. Cable, Ethernet cables. 100 or 1,000, which is equal to as 1 gig. If you buy a bit newer computers, they probably have a port that is ready to transmit 1 gigabits per second. 그죠? And then it goes to faster internet. Ethernet is reaching up to 100 megabits per second, which is a typical speed that you can get in your homes, your desktops. So simply means if you plug into another port with 100 megabits per second, theoretically you can exchange the bit information, right, at this rate. And it goes to gigabit, late 1990s. From Gigabit Networking Research Project, operate 1 gigabits per second. Actually nowadays go up to 10 gigabits per second, 40 gigabits per second. And some instances in a really, really big backbone, which is company's backbone. Sometimes they start using 100 gigabits per second for testing purposes. So in our school, I think these buildings are connected over 1 gigabits per second link, I think. But some other universities they have a 10 gigabits per second speed. So 빌딩끼리도, between the building, they have these lines in it. And the cables, after that point, the cables becomes not look like this. It they start using a fiber optic cables. Fiber optic cables. Fiber optic cable이 뭐지? 광섬유라고 얘기하죠. It is actually what? Fiber optic cable is actually a fiber, which means 유리섬유. So in these type of coaxial copper cables, I can do this, right? It doesn't really matter. I can bend, I can cut, doesn't really matter. But if you do this with the optical cables, you're actually breaking a glass. So you can't do it. So if you're gonna damage the cable, 이렇게 가끔 보면 광 케이블 되게 얇아요. 이거보다 한 10분의 1 크기. 이렇게 어깨에 메고 다니는데 가벼우니까. 근데 이렇게 마음대로 하면 안 돼요. 깨져. 섬유라서 깨져. 섬유 깨져. You actually transport light using the cables. Hopefully, I'm not so sure we have a picture of those cables, but something like that. So Ethernet is the most common technology nowadays, even in the backbone in our own use. Why Ethernet protocol was so successful? 이거 왜 되게 유명할까? Why in your computers they all have Ethernet chips in it? One simple reason, actually. There were other techniques out there too. Simply, it was cheaper to manufacture. 쌌어요. 가격이 쌌어요. Cost is much less than the other protocols like ATM, which you're not very familiar with. So this is a brief history line, dial-up 56. 아마 내가 이 전전부터 썼던 것 같아요. When I was in elementary, it was 5.6 kilobits per second modem. That was in my 한 7, 8살 이때쯤인 것 같아요. 기억이 잘 안 나는데. And then it goes up to like this ever since the DSL modem 2 megabits per second. Still, some part of the country we use that as a main feature in it too. Ethernet, gigabit, 10 gigabit, 100 gigabits Ethernet too. That's the time it takes to send one small image with 8 million bits. It's time so fast. You also hear this type of comparison in the Wi-Fi too, or wireless techniques, or wireless technologies. Like LTE, you can download certain movies within a second or stuff like that. New versions of Vibro 2, Vibro 3가 있나? I forgot. But there was Vibro 2 and LTE. I don't know what's going to beyond the LTE, but they usually compare. They usually highlight the advances in their technology by comparing the speed of the transferred data, images. So this is quite common. We know what it is. And there are other type of wireless data communication too, radio, microwave, infrared signals to mobile computers, which all you have. If you have a smartphone, you have infrared는 similar to 뭐냐? NFC, probably. What is NFC? Anybody paying your subway fees using NFC card? 혹시 핸드폰으로 지하철비 내는 사람 버스비랑? 지하철 안 타? 다 차 있어? 차 있냐고 전에 물어보니까 차 아무도 없더만. 지하철 안 타? 혹시 저 핸드폰으로, 스마트폰으로 내는 사람 없어요? NFC로 내는 사람 없어? 야, 이 시대에 뒤떨어진 사람들을 보았나? 카드로 내요? 물론 나도 카드로 내요. 귀찮아서. 핸드폰 꺼내고 하기 귀찮아서. 근데 infrared is very similar to 뭐야? NFC. NFC stands for what? Near field communication protocols. So you're only able to exchange the data if they are physically close by. Those are also protocols. Or easier protocols that you might heard is Bluetooth. Is also protocol names. A lot of people use Bluetooth for what? Listening to music. The Bluetooth speakers. 뭐라 그러지? hands-free sets. 그죠? Those are also actually called as a protocol names. Bluetooth 3.0, 4.0. There is actually Bluetooth for underwater. 그것도 어디서 본 것 같아요. Underwater Bluetooth. So they can use Bluetooth on underwater. If you water is not good medium to transfer the signals, but if you use those type of Bluetooth, it might be better. Anyways, microwave. microwave가 뭐지? What is microwave? 전자레인지에서 많이 나오죠. 그죠? How can you use this microwave to use for the internet connections? 인터넷 커넥션. 우리나라도 요즘엔 어떻게 하는지 잘 모르겠어요. 요즘에도 많이 할 거야. 우리나라, Korea. If you have an island somewhere here, they put micro antennas. Antenna facing each other. Then you can put the internet data on top of this microwave signals. So they can exchange the data. It's a bit expensive. Also, if the antenna is facing differently, then they will not guarantee a good bandwidth. 실제 안테나 이렇게 서로 마주보게 해갖고 마이크로웨이브로 그 전파를 사용해서 인터넷을 할 수 있게 하는 섬 같은 데 많이 하고, 섬에 요즘 이런 뭐로 많이 하죠? 섬에 뭐로 많이 하지? Satellite, anyway, satellite, like, so there are many different technologies out there for you to use wireless communication. Usually expensive, slow and expensive. Mobile computing, data delivery regardless of the location and blah, blah, blah. Bluetooth, we discussed. One of the main features for the Bluetooth technology was low power. Probably it's very annoying to use a Wi-Fi on your smartphone because of the battery duration. Why do you think the battery is running so much if you use a Wi-Fi? Or even Wi-Fi, for example, for Wi-Fi. Search signal, that's 30% right, yes. Search signal is correct too. It might be easier to understand if you know the basics of these protocols. Wi-Fi protocols, they are basically something called contention-based. Contention-based. So if you're sending your data, someone else try to send their own data. If they try to send their data at the same time, one must be waiting. Basic idea for that. So if are waiting for how long? So you keep trying until your data get through. Or like you said, we need to keep connected. So once in a while, I need to send some garbage data to stay connected. Those type of behavior will take a lot of batteries because it will ask for the applications to generate packets and memories, operating systems, blah, blah, blah. The things that we covered. Hopefully the contention-based protocols will come up later at this slide. Low power, close range, 30 to 50 feet, connected devices like wireless mouse, cameras, video games, blah, blah, blah. Wireless local area network. LAN is this is the LAN. Without W, it's a LAN. Local area network. We are connected to LAN. So that's why we sometimes call that cable as a LAN cable. You try to connect to the local network. Just among us. So if we are connected to the same local area network, same LAN, and if we are exchange the data, then we don't have to go out to the internet. We can just exchange within this local network, which is less work and easier to find between each other. Computers transmit wirelessly to base stations with the wired connection. So the Wi-Fi, you guys usually connected to the Wi-Fi connections, but that actually device, 공유기, is actually connected through a wired. Range is 150 and 300 feet. 저거 얼마냐? Someone divide by 3. 50? 50 meters to 100 meters. If there's no barriers in the between, if there's no walls and no interference in the between, you might be able to do that. What if you use a 100-meter long cable? 이거 100m짜리 케이블로 연결하면 잘 될까 안 될까? 해본 사람 없어요 혹시? 혹시 집이 한 1000평 정도 돼서 100m 케이블로 해본 사람 혹시 없어요? Usually 100 it will probably working but very slow speed. So even with that cables itself will have a certain limitations. 한 20-30m가 적당하고 너무 길면 갑자기 인터넷이 느려지게 느껴질 거예요. Signals are getting weaker. The signals, so at some point you need to boost up the signal so you can transfer further. 그 typical fiber optic cables that is used to connect connecting between buildings, like this building to the engineering building too. 그런 것들도 it depends on the cable types. Sometimes those ranges are up to 2 to 3 kilometers. If you use some other bit more advanced technologies, those cables reaching up to 10 to 20 kilometers. 10 to 20 kilometers. 한 아마 학교 정도에서는 한 2-3km 정도 가는 케이블 쓸 거예요. 그리고 실제 이제 길에 깔고 이런 거는 10km, 20km 이렇게 가는 광 케이블을 깔 거예요. Terminology is Wi-Fi. IEEE 802.11 that we discussed last class, wireless network stations. Anybody try to look it up, this IEEE 802.11 standard from the web, from the internet? Please do so. Type this up in Google, then you will find a lot of resources on this part. And then we usually call that as a Wi-Fi hotspot in your coffee shop. Starbucks, they usually provide a Wi-Fi hotspot. Metropolitan Wi-Fi service, cities provide routers. Blah, blah, blah. Routers? What is routers? 라우터가 뭐지? 공유기? 누가 공유기라고 했어요? 비슷해요. 그죠? But 공유기 is used in our household. You can think of as 공유기 is a dumber router. It's doing much less. But in actual router means this is a small computer in the middle. It looks like 공유기 NAT devices. But it knows where to send your data to. So it's like determining the path of the packets, data that you're sending in each other. So you can think of as a small computer with a routing capability, route finding a path. So hopefully it will come up again later. 어디더라? San Francisco, city like San Francisco, Google인가? They deploy thousands of Wi-Fi in the city of San Francisco, so citizens can use a free Wi-Fi. 그죠? 맞나? 아마 샌프란시스코인가 그랬던 것 같은데. 구글에서 공짜로 와이파이 다 깔아줘가지고 이런 거로 보면 돼요. 와이파이 핫스팟이 많은 거. 근데 can you deploy the Wi-Fi? If you have many Wi-Fi, is it always a better solution? Is it a good solution? Wi-Fi 많으면 어떻게 돼요? Wi-Fi 스테이션이 많으면 어떻게 돼요? 핫스팟이 많으면. 채널 간섭 난다고 많이 그러죠? 그죠? 일반적으로 와이파이뿐만 아니라 핸드폰 할 때도 이렇게 많이 해요. 그 통신회사 다니는 아저씨들이 차 이렇게 몰고 다니면서 왜 쓸데없이 이렇게 돌아다니냐면 그 채널 보느라고. 그래서 이렇게 예를 들어 안테나가 있으면 여긴 내 구역, 여기는 딴 안테나 구역, 얘는 좀 더 좋은 거라서 내 구역이고 이런 식으로 해요. 그래서 어디다 갖다 놓을지. 근데 잘못하다 겹쳤어. 서로 간섭이 일어나서 잘 안 되는 경우. 이런 간섭이 많으면 많을수록 돈은 돈대로 투자하고 품질은 품질대로 떨어지고 시그널끼리 겹치니까. 이거는 그래도 회사들은 이런 걸 잘 해요. 이런 소프트웨어가 있어, 프로그램 짜서 안 겹치게. 왜냐하면 이것만 알면 되니까. 최대 뭐 100m까지만 커버할 수 있는, 200m까지만 커버할 수 있는 이런 거로 제대로 할 수 있는 소프트웨어들이 팔아요. 잘 찾아보면. 여러분들 집에 웬만하면 공유기 다 있죠? 집에 가서 이거 한번 해봐. 아파트 사는 사람. 아마 층별로 공유기가 다 있을 거예요. 그래서 아파트에서 공유기 잘 안 되는 경우 많아요. 그럼 어떻게 해야 돼? 뭐 채널을 바꾸는 방법도 있고 너무 많은 방법이 없어요. 누구 하나 거를 가서 죽여야 돼. 진짜로. 방법이 그밖에 없어요. 시그널이 겹쳐서. 이것도 상당히 심각한 문제 중에 하나예요. So how to deploy the optimized Wi-Fi in the, especially building like ours, like apartment buildings that we live in. How to remove those interference between those small 공유기 devices, NAT devices. It's also a very hot topic to do it. 이거는 회사에서 지네들끼리 한다지만 집에서 하는 건 누가 한 명이 관리해 줄 수가 없잖아요. 그죠? 나는 어떻게 하냐? 나는 일단 내 거 와이파이를 숨겨요. 내 거 와이파이를 브로드캐스팅을 안 하게 한다 그러지. 내 와이파이가 있는지 몰라요. 일단 숨겨. 그래도 채널 간섭은 일어나니까 채널을 맨날 바꿔요. 좀 덜 겹치게. 꼭 누가 이사 오고 나가면 채널이 변경돼가지고 바꾸기도 하고. 아니면 더 쉬운 솔루션이 있어요. 비싼 공유기를 사면 시그널이 엄청 세요. 두 개를 쓰거나 이러면. 애플 거 같은 거 사면 시그널이 엄청 세요. 전자파는 책임을 못 지겠는데 시그널은 엄청 세요. 남의 거 죽여버리면 돼. 그래요. It's just, I'm just making easy, funny jokes, but it's a very, very important problem nowadays. Hackers actually, they drove around the apartment buildings and they try to find some Wi-Fi that is open. So anybody, people who is using the Wi-Fi device at home, do you guys put any password protection? How many of you get the password enabled? 1, 2, okay. Is your password ABCD123 or 1, 2, 3, 4, 5, 6, 7? 60% of password is like that. ABC123, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there is also a big problem. 뭐라더라? I read some papers, research papers. They say 70% of the Wi-Fi hotspots are open. They're all open. So anybody can connect it to use it. 가끔씩 어디 출장 가면 그래요. 대전 같은 데 출장 가서 갑자기 인터넷이 필요하면 물론 그때는 뭐 3G가 시원치 않아서 그러면 가까이 보이는 아파트 단지에 괜히 한번 차를 쓱 몰고 들어가면 와이파이가 많이 잡혀요. 그럼 그걸로 인터넷 쓰고. 와이파이 잡히면 그쪽 와이파이 들어가서 비밀번호도 바꿔놓고 주인도 못 쓰게 비밀번호도 바꿔놓고. 생각보다 할 수 있는 거 많아요. 한번 해봐요. 그거 한번 해봐. 재밌으면 한양대학교 와이파이 스테이션이 패스워드 뚫려 있는 게 몇 개나 있는지. 컴퓨터 이렇게 들고 다니면서 하루 종일 걸어 다녀봐요. 캠퍼스에 몇 개나 찾는지. Basic network concept continues. Wireless wide area network (WWAN). Computers transmit wirelessly to remote base station. Base station means station with the big antenna. So it can transfer. 일반적으로 이렇게 많이 그리죠. They usually draw it this way. 뭐 이렇게 그려가지고. Base station. So your mobile phones are connected. This one is connected to a router at some point through the landline cables like that. Typical representation of those network. Cellular technology antennas on the tower miles apart. 마일이면 miles apart. 몇 킬로, 2, 3킬로. When you guys watching the news, sometimes they usually say, if you call 119, then they can find out your location of the caller. 그죠? How do they find out? 맨날 신문에 나오잖아. 119에 전화 걸면 전화한 사람의 위치 추적할 수 있다고 얘기하는데 뭐 개인정보니 뭐니라고 못한다고. 근데 막상 찾으면 오차가 심하다고 나오잖아요. Why? Because it's maybe a kilometer range. So they can find out which base station you log into, but you don't know where. So it's only can find within the 1 kilometer radius, the color is here. So you don't have exact location of the color, but you can find out where is about the regions of those locations. That's why they call it as a base station. 맨날 뉴스 나오는 거 9시 뉴스에 맨날 나오는 거잖아. 이번에 세월호 뭐고 할 때도 학생이 전화가 온 게 베이스 스테이션에 이렇게 잡혔다 그러잖아요. 섬에 있는 베이스 스테이션, 섬에 있는 안테나에 단 바다 쪽은 조금 문제가 있어요. 바다 쪽은 장애물이 없어서 시그널이 정말 많이 가요. 빌딩 이런 게 없어갖고 그래갖고 진짜 책에 써 있는 만큼 가. 몇 킬로도 막 가. 막 10킬로 이상도 간대요. 무슨 모르는데. 그렇게 되면 반경 10킬로면 어디인지 어떻게 찾아? 그죠? Also, sometimes the Wi-Fi devices are helping to find the locations too. Sometimes they give you the GPS location through the Wi-Fi as well. So those are the stuff they usually mention in the newspapers and media reports. 4G voice and data transmit LTE 5 to 20 megabits per second, probably LTE plus. I'm not so sure about LTE plus. They say it's a plus, but I'm not so sure. I think it's more of a marketing term. So LTE could be more than 20 megabits per second. Signals may be blocked when indoors. Inside the buildings, those are the difficult things to find out. Errors with the transmit data can slow performances. A lot of factors are placing in this type of network. Security issues as well. What if someone hacked your packets because you transmit your data over the air? Anybody can listen to that air. 그렇죠? 옛날 CDMA 뭐 이런 거 얘기 많이 나왔죠. 그렇죠? CDMA가 뭐의 약자더라? 혹시 아는 사람? 코드 디비전 멀티플렉스 뭐 이런. 그 자기가 가지고 있는 똑같은 키가 있어야 자기 거를 딱 잡아서 알 수 있어요. 그러니까 이론상으로는 누구든지 다 들을 수 있어. 근데 그 키를 그 자기 거를 도로 알 수 있는 키는 되게 유니크해서 좀 어려운 얘기구나. 암호화가 된 거를 풀려면 또 뭐가 있어야 되는데 그게 너무 많아서 이론적으로는 뚫기는 불가능하다 그래서 뭐 도청이 불가능하니 뭐 이런 얘기 많이 했었어요. 지금도 뭐 마찬가지고. Security wireless signals easy to intercept or interrupt. You can block the wireless signals. 그 뭐야 예비군 훈련 같은 데 가면 훈련 받을 동안에 핸드폰 안 돼요. 방해 점퍼 막 쏴갖고 안 되게 갖고 딱 점심시간에는 딱 다시 되고. 아무래도 조금 힘들겠죠? 막기가. 케이블도 힘든데 뭐. 케이블도 쉬운데 뭐. 저거 어떤 나라에서 wireless wide area network, WWAN 어디서 제일 많이 쓸까? 요즘에. Which continent in this world use more of this WWAN technologies to build a backbone network of the countries? 제일 많이 쓰는 나라. 어디? 우리나라도 많이 쓰죠. 근데 우리는 끝에는 다 선으로 가요. 다 선으로. 그 베이스 스테이션도 다 선으로 연결이 돼 있어요, 결국에는. 근데 아프리카 이런 데는 선이 원래 없잖아. 선을 깔려면 돈이 많이 들거든요. 그래서 아예 깔 때부터 얘네로만 깔아요. 그리고 뭐 빌딩 이런 게 없어서 시그널이 잘 간대. 땅은 넓은데 수십 킬로씩 돼도 안테나 2개씩만 세워놔도 잘 된대요. 그래서 우리 비디오 보고 이런 것도 다 저쪽이 오히려 더 잘 돼 있다고 그러더라고요. 희한하죠? 그죠? LANs, wired connections, computers, printers, servers in close proximity. So they should be close by within maybe 100 meters, cables, limitations or whatever. So LAN is more of a local time. Example, same room. If you're in this building, we're in the same LAN. Of course, there are other type of LANs like virtual LANs, but those are out of scope of this course. Campus is also, in a way, it's a big part of the LAN. Private owned and operated topology, how computers are connected affect how they communicate. Topology is how your computers in a single LAN or in a network are connected. How are we connected to this Wi-Fi? Assuming that we all use a 한양인 WLAN. 그죠? 한양인 WLAN이라고 그러죠? Wireless LAN. 그죠? Wireless Local Area Network. If you try to draw that to a graph, how are we connected to that Hanyang University? There's somewhere in this building they probably has HY LAN. 이렇게 되나? WLAN이라고 그러던가? Wi-Fi device with antenna. U. Right? If you try to represent that as a graph, we are actually connected in this way. 그죠? We're not connected in this way. We can, but we usually don't do this. 그죠? So if you want to talk to this guy from this one, you have to go through this and go back again. It will come up with something called star topology. So at the top of the Hanyang WLAN, it will probably connect it to somewhere else, like that. If I give you a graph like this and ask you to apply the Dijkstra's algorithm from this point to there, it just create a networking problem with the shortest path. 그지? 이게 만약에 ITBT 이 방 이름 뭐야? 302, ITBT 302. Maybe that guy is engineering building 2, room 101. Can you find the shortest path between the two by applying the shortest path algorithm that we learned? 할 수 있을까? 모르지 뭐. It's not my problem. I'm not the one who's writing the final exams. 그죠? So we're gonna take a look at that. So topology is a term to describe topology. So it's like a map. It's like a map. Okay. So there are a bunch of other stuff too. Body area network is also one of them too. 근데 이거 this is a bit old slide now. See? If you take a look at 이거 옛날에는 if you put the sensors on body can transmit the electric signals too. Body itself is also 우리도 전도체잖아. 전기가 흐르잖아. Very small amount of electric. So they wanted to use our body to transmit the data between the devices. The watch to my cell phone if are close by. But this and there was a bunch of other devices are developed, but it's nowadays it's a joke, right? You can buy this type of devices with 얼마야? How much is a Galaxy Fit? Galaxy Watch 뭐라고 그러지? Galaxy Fit이라고 그러나? 기어 말고 Fit도 있잖아. 기어 핏이라고 그래요? 얼마야? 갤럭시 기어 얼마야? 한 20만 원 하나? 그죠? Galaxy Fit also had some sensors in it too. They can monitor your heart rate. 그치? So it's like you can use a body area network as to monitor ECG. 이거 뭐냐? 심장에서 나오는 시그널? 뭐 이런 거. Your Zigbee also one of them. Motion sensors too on your shoes. 이런 거 다 있지 요즘에. 그죠? 나이키 앱 같은 거 하면 신발에 달려갖고 다 나오죠. 얼마 뛰었는지 얼마 했는지 다 나오죠. 스마트폰에 자기가 뛴 이게 길도 쭉 나오잖아. 그치? 얼마 전까지만 해도 이게 막 논문에 나오던 건데 요즘엔 너무 쉬운 게 돼가지고. Don't worry too much about this type of GPRSs. You can think of it as a base station. 저런 거 좀 어렵고. 이런 것도 뭐 너무 요즘엔 좋은 게 많이 나와서. 옛날에 한 5, 6년 전인가? 대구의 어디 병원에 가니까 흉부외과 교수님인데 심장 수술 맨날 하시는 분인데 자기 환자들이 대부분 아픈 사람들이잖아. 심장이 아픈 사람이니까 되게 심각한 질병이잖아요. 근데 심장 수술을 해갖고 나오면 이렇게 그 교수님이 벤처 비슷한 걸 해갖고 이렇게 센서를 하나씩 이렇게 달고 다녔어. 핸드폰 그때 CDMA 2000 나올 때야. CDMA 2000 뭐 3G 넘어가기 막 전에. 그래가지고 자기 환자들이 걸어다니면서 심박이 이렇게 해갖고 계속 전송이 돼. 그 회사 모니터로. 근데 심장 그 수술 받으신 분들, 근데 심장이 이렇게 가다가 끊어지면 죽는 거잖아. 그죠? 시그널 이렇게 가다가 영화에서 나온 것처럼. 근데 그 모니터링 룸 가면 한 40여 분 환자분 그게 쭉 나와요. 화면이 40개가 딱 분할돼 갖고 막 이렇게 되고 있어. 맨날 끊어져. 맨날 끊어지고 있고. 핸드폰이 자꾸 끊어져 가지고 배터리가 죽고 그러면 끊어지면 119로 자동으로 전화하게 만들어 놨거든요. 계속 전화 가는 거야 119로. 잘못돼 갖고. 요즘에 그런 거 많이 나오죠. 앱으로 ECG 모니터링해서 갖고 많이 하는 거. Anyway, let's go back to this topology examples. So there could be few different type of topologies that we can take a look. First thing is bus topology. So you can think of it as a single node as your computer, your device, whatever. You could connect it in this way, bus. Bus is like what? 저건 뭐 같지? Bus topology. It look like CPU memory like, 그죠? Computer organization. So in those examples, then one must be wait another to communicate. 그죠? So you can take a look at it as slow to fast. Slow to fast. So shared lines, one line share, your computer is connected this way. So right at the interconnected lines, it says take turns using the line. So I have to wait. If this one is so take turn, 1, 2, this one first, and then the other waiting. This one's turn, the other's waiting to send the data using this bus. So it must be slow and maybe a lot of waste of the data that you are sending to. I like to send data whenever I want, but this way I may need to wait. So it will take a long time to transfer the data itself. So second one is ring topology. If I wanted to send certain messages to someone else in the local LAN, I have a message for this guy. So maybe there is only one way around. Maybe I can send the message this way only. This guy, take a look at that message. This is not for me, pass. 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 This is for me, received. So you send the message data, small data, in the one way to circle around to find the destination node. Slightly better, but it will be still slow. Also, you can have a token. So if you have it's more of a take turn. If this is my turn, I can send whatever. Also, there is another way of doing it. 토큰이 이게 더 맞겠다. Bus is the right way to do it. So star topology, all sent to a central node, which is router to destination. Star node. Star topology, star. If I have a certain data to send, I send it to the one guy in the middle. And this guy will find the next pass from this point to somewhere else. In the IP environment, current network, maybe they look at the IP addresses. If I take a look at this guy's IP addresses, this guys need to go this way because they request information from outside the campus, so let it be. 이게 좀 낫죠? So current internet is more of local LAN is based on this way. 이렇게 다 붙어 있으니까 알 수 있어요. What might be the potential problem of this star topology? Potential problem of this star topology. 문제가 뭘까? 꼭 스타 토폴로지의 문제만은 아니지만 일반적인 어프로치 문제는 뭘까? 문제가 뭐야? 찍어. 모르면. 이거 바꿀게. 문제가 뭐야? 문제는 여러분들입니다. 그죠? 이 문제하더라. 문제는 one of the potential problem of this topology is what if this guy dead? Yeah, this one will be disconnected, right? It's a single point of failure problem. So there is a single point of failure. We'll have everything will be failed. So it's nice way of organize the network, but it's have a potential problem of single point of failure. This is not the only. This is one of the common problem of the networking structures. Distributed systems are discussed in order to overcome the difficulty of single point of failure. 그렇죠? 뭐 얘네도 비슷하긴 하겠지만, what if this guy dead in a circle? So also get disconnected. This guy dead, but should be okay, but still be alive. Anyways. 아이고. Sorry. Ethernet LAN cables with a shared cable. So we are sharing this cable. Bus topology, single cable over short distances, multiple cable over the long distances. Repeater amplifies the signal, bridge router, message only when necessary. 뭐 이건 다 치우고라도. How can we send a? Each cable has a limitations of how long, the physical distance of they can transfer a signal. So after you send a signal, you like to send it longer. Then you put an extra device like repeater, amplify a signal, amplitude that we looked at the signals. You can increase that signal, 증폭시켜서 travel another distance. 예를 들어 1km짜리 케이블은 1km만 딱 보낼 수 있다고 쳐요. 근데 실제로 가야 될 건 예를 들어 2, 3km야. 그럼 1km마다 리피터라는 장비를 붙여가지고 시그널을 한번 크게, 시그널이 계속 가면 이렇게 작아지니까 소리 가듯이 작아지잖아. 작아질 때쯤에 한번 다시 키워서 보내주고. Repeater is the one. Bridge. So you consist your network in this way, bridge or repeater like. So if somewhere in C need to send the data to B, you organize your network. The C must be going through this bridge. Separation is also possible. Physical or logical separation in the two. 예를 들어 여기서 중요한 일을 하는 사람들이 있어. 여기 알려주면 안 돼. You can protect the network by killing this one. No interconnection between two. So those type of organization is also possible. So that's why they call it as a bridge. 이 그래프에서 이 둘 사이 끊기면 이 둘 사이에 갈 수 있는 길은 없어. 그렇죠? 그렇게 구성할 수도 있고 그렇게 많이 구성되어 있어요. 예를 들면, what if we cut the line from this building to engineering building 2? In the engineering building 2, there is a main computing center which can go out to the internet. So if we cut that line, we cannot go out to the internet. We can only communicate among ourselves. 그렇게 보면 돼요. Bridge is the way. 뭐 그러나 똑같지 뭐. Ethernet LAN with the switch bus topology, still shared cable inside the switch. Wiring closet contains a switch and ports. Ethernet jacks in a room connect to the switch in the closet. Wireless base station also connect to the switch in the closet. 이거 무슨 뜻이냐면, somewhere in this building there is probably a room with the closed doors, locked all the time. If you enter that room, there is a switch, bunch of switch are operating. So your connection, this cable probably connected to one of those ports. Also, all those Wi-Fi base stations are connected to that switch. 스위치 어떻게 생겼나? 스위치가 어떻게 생겼을까? 볼까요? 스위치 그 공유기 어떻게 생겼지? 공유기 뭐 한 2, 3만 원짜리 사면 이렇게 생기고 유무선 공유기면 한 4개 이렇게 들어가게 생겼죠. 스위치 12, 24, 36, 48. 그게 스위치예요. 구멍이 24개, 48개까지 들어가고 할 수 있는. 그거 공유기를 이만큼 키워놓은 거라고 보면 돼요. 실제로 그렇게 생겼어요. 애누리 들어가서 봐. If you don't know anything, if you don't know what it is, try to look for information 애누리. That might be easier. 애누리에 가면 스위치 구매 이렇게 돼 있어요. 뭐 얼마더라? 얼마 전에 다른 과목에서 들어가서 봤는데 뭐 한 24개짜리 뭐 한 2, 30만 원? 좀 싼 거는 2, 30만 원 이래요. So this is graphical representation of what was discussed in the previous slide. So room 101, this is maybe our room has an Ethernet interface. This cable that it comes out. This cable eventually connected to one of those switches in that other room. This switch will be connected somewhere to the internet. So main computing center, for example, main computing center of this campus. Then you can transfer. Also, this type of Wi-Fi AP access point are connected to this switch, and then you will be able to connect to it. So that's typical structure of the switch. Wide area network is a bigger network. It's like you're connecting between states to states. 아니면 우리 같은 경우에는 뭐 서울하고 경기 있는 거. LAN is connecting between small rooms and small buildings, but WAN is the wide area network is connecting between two different cities. So it's connecting between two different cities. Sometimes they call it as a POP, point of 뭐더라? Point of connection POP이라고 그러는데 하여튼 뭐 100기가 라인들끼리 도시하고 도시. 예전에는 전산원이라고 있었는데 서울에 이제는 아마 다 대전인가 용인인가 갔을 거예요. 거기 가면 서울 시내에 있는 각 관공서에서 나오는 SKT, KT에서 나오는 케이블들이 그 빌딩 하나로 다 모여요. 다 모여요. 그래서 정부 무슨 보호 시설인가 이런 데 다 모이면 이제 스위치들이 많아요. 그래서 막 꼽고 빼고 막 그래요. 자기네들끼리. 킥스라고 많이 하죠. 킥스. Korea Exchange Point. 그래갖고 많이 썼는데 지금은 아마 서울에서 다 이사 갔을 거예요. 그 빌딩에 예를 들어 전기가 갑자기 나간다. 그럼 서울 시내에 있는 관공서의 인터넷은 갑자기 다 안 되는 거예요. 그런 식으로 보면 돼요. So wired connections, computers located at great distances, examples across the state or country or cities, dedicated point-to-point lines, point-to-point lines. Computers connected to other computers on individual lines. So routers between Gyeonggi and Seoul City, single line, are connected. Store and forward packet switching. Packet, when I was keep referring to a data to send. Actually, you are actually making a packets. Small unit of the data that is created from your computers to send. 패킷을 한번 볼까? 패킷이 어떻게 되는지. 여기 와이어샤크 깔아야 되는데. Maybe next class I will install a Wireshark in this computer and then I will show you how to look at the packets. It's basically all you know. HTTP web browser packets will contain the HTTP protocol and IP addresses. It's a way of take a look at the contents of the data that you generated or you're receiving. 깜짝이야. So it's still, if you have a topology of your network, it's actually quite difficult to have the entire topology of this, even for this LAN. If I ask you to discover the topology of this building, network topology of this building, it would be quite difficult to get the exact image of it. But imagine that once we have that, we like to find the shortest path. Sounds very familiar to the Dijkstra, right? Routing of the packets determined dynamically. So this is a source, this is destination. Common questions are which path to take from source to destination. So from the source, I send a small data packet. It could go this way or this way, I don't care. And at the B can make a decision to where to send it to. It has a choice for C or F. F, C. From F, you can go either E or D. Hopefully, you can go to D, C from C too. So there could be a multiple paths that single packet can take. You can think of this as your computer. It's another computer, but they only looking for a path for a certain data only. So this is desirable. Redundant path is good for fault tolerance. What if the connection between B and C got interrupted? No connection between B and C. Then I may be able to take another path from B to F, F to D. So this is what internet is the current internet architecture look like. So it's not always the shortest path. We all, among the many multiple paths that we can take, maybe we choose the optimum one at the time being, but if that path got disconnected, then there should be also other choices that you can take. So in a way, maybe you run a Dijkstra's algorithm on this graph, and you remove this line between B and C. You run your Dijkstra algorithm again after a certain thing happening in this graph. 근데 in order to run a Dijkstra's algorithm, what was the precondition they suggested? 몇 개 precondition이 있었지만 in order to run a Dijkstra algorithm, you need to have a complete graph first. You need to have a complete topology first. But the internet architecture, in the current local LAN, do we know the complete topology of the connection? 이 빌딩 안에서도 정확하게 알기 힘든데. 예를 들어 이게 몇 호지? 302호에서 508호로 있는 친구한테 메신저로 왔다 갔다 할 때 그 패킷이 어느 길을 통해서 가는지 100% 확신할 수 있어요? 잘 모르죠. 근데 Dijkstra 알고리즘은 그래프가 완벽해야지 거기다가 알고리즘을 런을 해서 하죠. 그죠? 응? 변하면 사용할 수, 자주 변하면 자주 해야 되겠죠. Dijkstra를. 근데 Dijkstra의 문제가 뭐였어요? 한 번 하는데 시간이 노드가 많아지면 컴플렉시티가 높다 그랬죠. 그죠? 매번 그렇게 할 거냐? 굳이 매번 그렇게 하지 않고 꼭 매번 짧은 길은 아니어도 되니까 비슷한 길이 있으면 글로 보낼 거냐? 그죠? 여러 가지 디시전을 할 수가 있겠죠. So just don't mix up. Just because we discussed for the Dijkstra algorithm, it doesn't mean that current internet pathfinding always uses Dijkstra. It's just one of the suggestions. And some protocols do actually use the same ideas, but there will be a lot of restrictions. Like you must have a complete graph first. You must have a non-negative edges, things like that. And hopefully it's not changing a lot, so you don't have to apply over and over again due to high overhead. Redundant path is what we require, what we desire for the internet architecture. So responsive to the traffic load. 여기서 이건 뭘까? Responsive to a traffic load. Might be equivalent to the weight on the edges. Dijkstra 할 때 여기 weight 있었죠? The value. So maybe from B to C it takes 1 second. Depends on how many people are using this network. Sometimes it's taking longer than 1 second. So that weight value may change all the time as well. So hopefully you can see that how difficult it is to keep applying to applying this Dijkstra algorithm in the actual examples. 혹시 질문? 오늘 거에 질문 없어요? 수고하셨습니다. Thank you.